How's it going, everyone? Stefan here. And today we're going to be talking about sieving and I guess modeling the clearance of impurities from UFDF. So here, on the left, I have a close-up image of what would be your UFDF filter. In these blue circles, we have your product. Maybe it's a protein, maybe it's a virus or an LNP, who knows? And these little green circles are an impurity that are being, clearly passed through the filter. But your blue circles are clearly not being passed through the filter. You can see there's none of them on the permeate side. So we can define a coefficient called the sieving factor, which is equal to the permeate concentration of your solute of interest divided by your retentate concentration of the solute of interest. So in the case of our protein in the blue circles, we could say sieving is 0. And that's because there's nothing in the permeate, so the permeate concentration must be 0. For something like our green dots, well, it's really hard to say from this image, but, sieving is greater than 0 for these green ones. And I'm just going to circle that in green so we know. The sieving must be greater than 0. If these green dots are passing freely through the membrane, we can say that sieving is equal to 1. In other words, just a little, therefore thing here. In other words, we can say that the permeate concentration is equal to the retentate concentration for those green dots. But I mean, maybe it's not. Maybe it's a little less. Maybe it's only a third or a half, or who knows? It could be anywhere. But that's what I intend to demonstrate, I guess, in this plot right here. Okay. So we can see that when sieving is 0, meaning that none of your solute of interest can pass through the filter, we increase during concentration, and then during diafiltration stays flat. And then when we start concentrating again, we increase. Okay. Pretty clear there. That's sieving of 0. So pretty much where it stays flat, you can see that we're doing diafiltration. But if sieving is 1, this lower one here, we can see that during concentration, the concentration of it stays flat. But when we start diafiltering, it decays really quickly to 0, really quickly. Okay. And then, of course, there's intermediate positions. For example, this green line where we have sieving is 0.141. During concentration, the concentration of the solute increases, but as we start diafiltering, it's decreasing. And then we start concentrating again, it increases. Okay, so the sieving of your solute of interest, if it's 0 and it's fully retained, you can see that the concentration is going to increase or stay flat. But if it's greater than 0, it'll increase to some degree and decay over the diafiltration step, and then increase again during concentration. But if it's equal to 1, it'll stay flat during your concentration steps and decay during diafiltration. So those are the extremes that are possible with, depending on what your sieving factor is. Now, I'm going to move this out of the way. Now, your sieving is equal to CP over CR. I'm actually going to just circle that again in blue. It's equal to the concentration in the permeate over the concentration in the retentate. So if you were trying to measure sieving, measure S, you'd say, well, I'll just take, measurements of my solute of interest in the permeate and in the retentate. But something I've often found is that your permeate concentration is too low. That is that your permeate concentration is less than the limit of quantitation of the assay to detect the solute. So what do? Well, I'll only measure the permeate concentration instead. That's how I've kind of solved this issue. I've just measured the permeate concentration. Well, if you do that, how do you measure sieving? Let's get into that. So if you're only measuring your retentate concentration, we can look at this C. That's your retentate concentration. I'm just going to put a little R next to it so we remember that's your retentate concentration. Well, we can measure our retentate concentration, right? And then we have a few different equations that may describe our retentate concentration depending on what we're doing. So this first one here we have is that's a fed batch concentration. Okay. What's going on there is we are effectively, running TFF as we all know, but as you're adding material into the retentate vessel at the same rate permeate's being removed, but the volume that you're adding into the retentate vessel, it's not buffer, it's more feed material. It's more of the same feed material. So ultimately, it's a concentration step. And you'll see in this expression here, there is an R. Well, the R is what is known as the tank ratio. And that is your total volume over the volume that can be held in the retentate tank, or the volume that's in your retentate tank. That's R. Okay. This is your R. So if the volume total, we can put a little T here so we know it's total volume. If this total volume ends up being equal to the retentate tank volume, V tank, R is equal to 1, and we move into this next step here, just a batch concentration. That's what that is there. It's a batch concentration. This here is batch. This is a batch concentration. This is where we are just removing volume from the permeate and nothing is getting added in to the retentate vessel. Now, there's an important distinction between these two that I hope to show in this plot here. So I'm going to draw in green. What you can see is that in a regular concentration, as your concentration factor increases, you get a linear increase. But if you're in that's for a batch mode. But if you have a fed batch mode where you're effectively adding in more product as you remove volume, your concentration kind of increases faster actually until you hit batch mode, which is here. That's where your retentate, or excuse me, your R, your tank ratio ends up equaling 1. And then you continue on your linear increase. Depending on how big your tank ratio is to start, you'll get curves that look, they increase much faster. Let me draw that in orange. So If your retentate tank ratio is bigger to start, you'll get curves that look more, they increase even faster, like these orange lines that I'm drawing here. You'll get things that look like this. They'll go even higher faster. Okay. Now the last mass balance that I have here, phase for modeling your retentate concentration, is this guy here. Okay. Now this is for dye filtration. Dye filtration. Okay. This is for dye filtration. So you're in dye filtration, you're effectively adding, it's like fed batch, but instead of adding a liquid or like volume that has more product in it, you're adding just buffer or something. So effectively, like as you remove permeate volume, you're adding more buffer in. So the volume in the retentate tank is constant, but you're not adding more product. No more protein or whatever your solute is being added. You're just adding more volume. So this is dye filtration, and it will describe the concentration in the retentate of your solute of interest. Okay. N in this case is the number of dye volumes. That's the number of dye volumes. So all of this to say, what I will do when I'm trying to measure sieving, and I'm only measuring the retentate concentration, I will use these mass balances that we've just discussed here to model what the concentration in the retentate should be. Okay. So now I am going to share another screen. Okay, I'm going over to Spider now. You should be seeing a script I wrote that is used to model the sieving. I'm not going to go through all of this line by line, but what I will show you here is if you were to use the script, and if you want to copy this, feel free, go ahead, pause the video and write down what I have here. But as you are, looking to model or determine sieving, this is what you're going to want to change. I'm going to show you. So you're going to want to put in the concentration of your solute of interest, what those values are. Okay. And this is what I've highlighted here. This is a concentration of your solute of interest. And then you're also going to want to put in what the permeate volume is at the corresponding measurement in the retentate. So what I've labeled here is fix. That is your retentate. This is your retentate concentration. And these are the corresponding permeate volumes. The last thing you'll want to change here in this script is the starting concentration, C in it, the number of, so that's this. This is C in it. You'll want to put whatever your measured starting concentration is, your number of dye volumes used in the experiment, the tank volume, the volume of the retentate that's in the tank, V initial, V init. Sorry that those little tags keep popping up. V init. This is the amount of volume you start with total. And then the volume reduction factor for your first concentration. This assumes that you have two concentrations, that you go from concentration to diafiltration to concentration. So this would be your first concentration factor. And then VRF2 would be your second concentration factor. This would be from your diafiltration concentration to the final one. If you don't have a second concentration, this can be listed as 0. Okay, you can list this VRF2, you can just type in 0. And what I'm doing here, you'll notice is I have like 9.1 divided by 3.5. That's all I'm doing is my total volume reduction, which was 9.1, divided by my initial volume reduction, which was 3.5, to calculate what that second volume reduction was after diafiltration. So I'm going to keep scrolling down here because there's more code that you might want to pause and copy if you want to use this script. And then down here, I have like all of this down here. These are all different plots that I'm going to make, and you'll see in a second. There's certain stuff you can change in here, like where it says X label and Y label. Maybe you'll want to change these to say something different. For example, down here in the Y label, and down here in this Y label here, I have impurity concentration in nanograms per milliliter. Maybe you have different concentration units, and maybe you want to actually name what this impurity is. And that applies to, these labels down here as well. Yeah. So I have some dummy data in here for an impurity at different permeate volumes. I'm going to highlight that. Remember, this is data that you'll change. This is experimental data. I'm going to run the code, and we have, comparison of fed batch and batch, which I showed you earlier. Another comparison of what the concentration will look like depending on the sieving factor. You saw one of these earlier. Those are pretty standard no matter what you put in for what I have here. But now here's the most important stuff is we have a plot of the predicted values based off the mass balances I've shown you versus the measured, and then an R-squared value. Of course, you want to see this look, linear, because it's your measured values of your solute of interest against your predicted from the mass balance model. Next, we have the actual plot of the concentration against the permeate volume using the mass balance. The mass balances that we just went over: the fed batch, the batch, and the diafiltration. And you'll also notice that in the title up here, we have the predicted sieving factor for this particular impurity. It's predicted to be 0.141. Okay. And then finally, we have here the sum squared error. So this is just the squared difference between the model and the predicted concentration values against the measured concentration values for a predicted sieving value. And, the model is going to select wherever this sum squared error becomes a minimum. So with all this that I've gone over, what you can do is you can measure the sieving factor, the clearance of a certain solute in your process stream, by taking retentate samples at different permeate volumes. So you'll record the permeate volume at which you sample, and you'll get some concentration of that sample from whatever assays used. And then you can effectively model that clearance over the course of the unit operation purely by entering in the concentration, which I've listed here as fix, and then the corresponding permeate volume in vol. And you'll need to record the initial permeate volume, or excuse me, the initial solute concentration, the number of dye volumes used, the tank volume, or the volume of your process fluid that's in the retentate tank, the total amount of process volume, and then of course your concentration factor before diafiltration, your concentration factor after diafiltration. And then before I wrap this up, I'll note that if you have batch concentration all the way through, there's no fed batch. Well, you can just make the V initial, V init, the same as the same as tank vol. These two numbers highlighted here can be the same, and you'll simulate a situation where it's just batch concentration for your first concentration. Yeah, so I hope that this, helps you determine your, sieving factors moving forward if you need to do so. I hope you can use this script. I'm just going to scroll through it one last time. So if you want to like pause and copy what I have here, you can do so. You can make these same plots. Yeah. And, some people may ask like, well, can't you, let me go back to the whiteboard really quick. Okay, let me go to the, okay. So hopefully you can see the whiteboard. Let me go to the mass balances. So some people may ask, okay, well, why don't you just use, let me see, where's my highlighter and stuff? The same thing has happened. Okay, so why don't you just use this equation here? You have your initial concentration and your final concentration. You know the number of dye volumes N. Why don't you just use that? Well, you can. You can just use that. You can have two concentrations and estimate your sieving factor based off your starting concentration, C naught, and your final concentration, C, and your number of dye volumes. You can calculate S. Okay, you can definitely do that. And oftentimes it's going to be extremely close to the mass balance values that we just went over. The difference is, or like the value add from doing it the way that I showed using the mass balances, is that if things change, like your input mass or concentration of impurity, or the concentration at which diafiltration is performed at, or your final concentration target reached, you can model all of that. You can see what your impurity levels are given all those different situations. However, if you just use this equation here, you're only going to get your starting and final values, and you can only look at it if it is you can't understand what's going on during the process. So what I typically do is I use the mass balances as described and shown in the script, but I'll also look at what this equation here predicts, and I'll make sure that they're similar. If they're not similar, that's telling me something's wrong. And if they are similar, I, everything's good. But if I can use the mass balances, then I have the opportunity to, um, predict or model what the impurity concentration looks like under situations where there's variability in how the process is being operated. So I personally find more value in what I've shown earlier and what's shown in the script. But I've also found you know really good agreement with what this equation here describes. So yeah, hopefully this was helpful for you guys. And if you ever need to measure your sieving coefficients, I hope that script can help you and you can model impurity clearance across your UFDF steps. Again, if anything wasn't clear or you have any comments or suggestions on how to improve any of this, just drop a comment and I'm happy to discuss TFF with you. And in fact, I would really love to do so. So thank you.